Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. When you hear a sound high in the atmosphere, you usually assume it's thunder, the explosive result of lightning superheating the air. But what if the atmosphere itself, without visible lightning strikes, was capable of generating acoustic shock waves strong enough to rattle aircraft or disrupt sensitive satellite communication? This is the core mystery behind a phenomenon scientists are increasingly studying, the Piezoturbulence Effect. Imagine a storm not of wind and rain, but of sound, silently brewing kilometers above our heads, powered by the most mundane force imaginable, static electricity. To understand piezoturbulence, we first have to look up, way up, into the region where high-speed jet streams meet the frozen veil of the upper troposphere and lower stratosphere. This region is a natural generator of charge. It's filled with microscopic particles, primarily ice crystals and frozen aerosols. When high-speed wind shear slams these particles against each other, a process known as the triboelectric effect, massive charge separation occurs. The triboelectric effect is what happens when you rub a balloon on your hair. But in the atmosphere, the scale is colossal. Instead of generating a small static spark, the atmosphere builds up a massive, localized electrical potential due to the sheer volume and speed of the colliding ice crystals. Crucially, this charge buildup happens rapidly and locally, often in areas that look perfectly clear to the naked eye and radar. This is where the piezo part of piezoturbulence comes into play, referencing mechanical stress, the turbulence and collisions, creating electrical potential. Standard lightning is a massive, visible discharge designed to equalize the charge difference between a cloud and the ground, or two clouds. Piezoturbulence works differently. Instead of a single, massive bolt, the intense localized electric field generates myriad tiny, high-frequency discharges within the air pocket itself. These micro-discharges are not powerful enough to be seen as traditional lightning, nor do they typically equalize the entire system. However, each micro-discharge instantaneously heats the surrounding air. When hundreds or thousands of these minute explosions occur in rapid succession within a confined, highly charged volume, they create intense, localized pressure waves, acoustic pulses. These pulses accumulate into what we term an acoustic storm. They are essentially localized zones of extreme sonic vibration and turbulence, hence, piezoturbulence. Why is this effect so difficult to study? Because it is often confused with clear air turbulence, or CAT. CAT is typically caused by wind shear alone, the physical mixing of air layers moving at different speeds. Piezoturbulence, however, adds an electrical dimension. An aircraft might encounter CAT that seems excessively violent for the visible atmospheric conditions, and that violence is amplified by the accompanying rapid-fire acoustic pressure waves generated by the static discharge. While CAT is purely mechanical, piezoturbulence suggests a hybrid mechanism, mechanical stress creating electrical stress, which then returns kinetic energy to the atmosphere in the form of sound waves and intensified localized shock. Researchers are using highly sensitive acoustic sensors and specialized E-field monitors flown on research balloons and high-altitude drones to differentiate these phenomena. The signature of piezoturbulence is distinct, a high-frequency acoustic rumble, often outside the range of human hearing, directly correlated with spikes in the localized electric field intensity. The implications of understanding and predicting the piezoturbulence effect are significant, particularly for aerospace engineering and satellite stability. These intense, electrically generated pressure fields could explain unexpected navigational errors or unusual vibration feedback reported by pilots flying through seemingly mild weather conditions. Moreover, the strong electromagnetic fields associated with the charge buildup can interfere with sensitive radio and satellite communications. Future advancements in atmospheric monitoring hope to integrate both mechanical turbulence detection and electrical field mapping to create a comprehensive early warning system. By identifying zones where high-velocity airstreams coincide with particle composition conducive to the triboelectric effect, we might soon be able to forecast these high-altitude acoustic storms. This would allow air traffic controllers to adjust flight paths, ensuring smoother, safer journeys, and helping us truly understand the complex, energetic relationship between mechanical motion and electrical potential in our dynamic upper atmosphere. The Piezoturbulence effect reminds us that the vast expanse above us is anything but silent, and that even the simplest forces, like static electricity, can orchestrate powerful, unseen storms. For more incredible facts like this, don't forget to subscribe and turn on notifications.